Okay, so we're going to start Unit 6, which is all about phases and the different properties that our phases have. So if you recall from middle school and elementary school, there's three phases: solid, liquid, and gas. And when we change between those two or undergo a phase change, that is just a physical change because we're not actually changing the substance. We're just changing how much energy is associated with them, with the molecules, and then the space between the molecules. That's really the biggest difference between solid, liquid, and gas. So there's a couple types of solids. There's amorphous solids and there's crystalline solids. Amorphous solids don't have a pattern. So if we look at the glass picture here, we can see that there's irregular shaped circles and they're not identical. And so that's an amorphous solid. Where if we look at something like quartz, it's very patterned. There's a distinct pattern to it. And so that's a crystalline solid. So amorphous is no pattern. Crystalline has a very specific pattern. Now, the only amorphous solids that you have to remember are glass and plastic. So glass and plastic are amorphous solids. Sometimes they're referred to as supercooled liquids because that's kind of how we make it. We put it in the liquid form and then we cool it down super fast. And that kind of freezes them in these irregular patterns. Crystalline solids, have that very distinct pattern. And so there's different types of crystalline solids depending on what the pattern is made out of. So the first one is ionic solids. There is a lattice point, or at each of the lattice points, there's an ion. So the lattice is the pattern that's happening here. So this is sodium chloride or table salt. So we have Na and Cl. Na plus, Cl minus, creating those ions. And there's a repeating pattern to it, right? One sodium, one chlorine, one sodium, one chlorine, one sodium, one chlorine. So that's the lattice that, or the unit cell, and then repeating it makes this lattice. And it's held together by the electrostatic force between the cation and anion, meaning there's an attraction between the positive and the negative that's holding that together in place. Some properties: they are hard, they have high melting points, but they're brittle. So if we hit this with a hammer, what happens is the two positives will line up and then they repel each other. So that's why it's brittle, because it breaks apart very easily. Metallic solids have a metal cation at each point. So up here in our picture, we have our metal cation, and then our electrons, remember, in metallic bonds are delocalized. So we have the electrons kind of floating around wherever they feel like going around. So it's held together by that sea of electrons. It technically is the electrostatic force between the electrons and the metal cations. But when we hit it, those metal cations, even though they might line up, they have those electrons in between to buffer it so they don't repel each other. So that's why metallic solids are not brittle, but they are malleable, so we can bend them and shape them, and they're ductile, so we can pull them into a wire. They also conduct electricity as a solid. Ionic does not conduct as a solid, just the metal solids, and that's because of those free-moving electrons. The third type is a very special type called giant network covalent. These are very specific to silicon-based molecules and are allotropes of carbon. Allotrope just meaning it has a different structure. So if we look here, here's graphite, that's what's in your pencil. And those are all carbon atoms. Now, if we increase the pressure and heat, we can transform that into diamond, which is over here. So it's a tetrahedral shape because there's 4 atoms attached to each carbon. So that's what an allotrope is. Silicon dioxide is right here. That's actually sand. So that's another type of network covalent. So at each point of our lattice, we have a nonmetal or a metalloid if it's silicon, and they're held together by just covalent bonds, those sharing of electrons. They're very hard, they have high melting points, and if it has delocalized electrons, then it will conduct electricity. So our pencil lead or graphite has those delocalized electrons, so they actually conduct. So don't stick your pencil in an outlet. But diamond and sand do not conduct because they're missing those delocalized electrons. And then we have our crystalline solids. These have an covalent molecule at each point. So this is water. And so you have the oxygen and then the two little hydrogens there. And those ditty dots there represent that hydrogen bonding, that force of attraction. So what's holding our covalent or our molecular crystalline solids together are those intermolecular forces that we talked about, London dispersion, dipole-dipole, and hydrogen bonding. They are very low melting points, but they are considered soft, and I know that's kind of crazy to think about a solid being soft, but what we just mean by that is they're not as hard as metallic and ionic and network covalent.